Okay, so since the screen is down for the quiz, let's do a couple of demonstration observations using the screen, and then put the screen up. So let's see, let's get some help. Have you guys all helped?
I haven't.
You have not helped? Come on up for a second then. Yeah. Okay. And you are?
Jacob.
Jacob, hi. Roger McWilliams. We should have used him for the latter one, huh? Okay, so, all right, Jacob. So what I'd like you to do is come on up around over here to start, and then describe to people what you see. And they should be able to see some of it up here as well. Okay, so let's start here so they develop a common bond with you and a trust for what you tell them. What do you see?
It looks like a bunch of little arrows.
A bunch of little arrows. Okay. And
Seem to be made of metal.
made of metal. What's that?
Really big magnet.
A big magnet. Okay, why don't you draw it near and see what happens? Whoa! Okay, so these little arrows are free to pivot, and very little friction anyway. And then they seem to line up with magnetic field made from this large permanent magnet, which has how many poles? Dipole, 2 poles, right? And in a dipole for electric charges, how does the electric field fall off as you move away from the dipole? 1 over r cubed overall, and then some angular dependence factor as well, right? Some sines and cosines. And so this is a dipole magnet, and if it's in close, it's a very strong effect on them. Now pull it back, and it becomes weaker. So the field falls off as you move away from the dipole magnet also. Wasn't that exciting? Okay, so now they can see what's on the screen. Why don't you describe what's happening past there over to here?
Past it, there's 2 wires, and connected to each wire is this copper rod that's passing right through the center of all the little...
Okay, so you guys can see on the screen the top of the copper rod, and then at this point it goes vertically down, so you can't see that so well unless we tip it to show. All right, so the copper rod comes along at the top where my finger is touching it, which is the bottom right now of your drawing, of course, and then it goes down, vertically down, and then comes back at the bottom of the device, which is down under here. You can see that's the bottom because I'm under it now. And then comes back over. And what are the colors of the wires that we've got?
Red and black.
Red and black. Do you think that the red conducts electricity better than the black, or the black conducts electricity better than the red? It has no effect at all that I know of. These are just the colors of the insulation on the outside. There is a non-conducting material put on the outsides of wires so that they don't short to something other than going to the wiring you want. Right now we have red connected to red up here and black connected to black, right? It's a common convention to use black as the lower voltage and black often as ground, and then red is the positive voltage, and it's not required to do that, it's just commonly done. And that helps electricians understand when they get to one end of a wire what it was at the other end so that they wire it up the right way. And then when you get lots of wires going, people put little paint codes on them with all kinds of colors. So it's easy to tell them apart. Okay, so over here we arrive at, and this is the excitement. The excitement builds for Jacob. He can hardly contain himself now. What do we see here?
A bunch of knobs.
Yeah, and some ancient power supply, right? Okay, and it has a switch. And then what does it read? Can you tell what it reads?
Volts and amperes.
Volts and amps. So some kind of power supply. We've got the wires hooked up to it. And Jacob is now going to, let's see, not yet. Let's see if we can improve our light a little on the arrows. Okay, so you see how the arrows are lined up right now. Let's just remind ourselves that they're free to move around. Okay, so we got the arrows all doing this. Okay, now throw the switch. Let's see what happens to the arrows. What happens? Can you see the pattern for the arrows?
Somewhat.
It's going in a circle around. See how the arrow points and goes this way? And there's a general pattern of the arrows encircling this wire now, right? Do you see it?
Yes.
Okay, good. That was a very confident yes. Okay, so turn it off. What we've just seen then is that electric currents make magnetic fields, because we've seen the reaction to the compass with the permanent magnet, and then we made the same thing happen with the electric current flowing. And by the way, why don't you read the volts and current on there to people, turn it back on, and then what does it say for volt and current?
Volts is below 0, actually.
Below 0, going the other way, okay.
And
The current is
off the charts.
off
above
the
15.
charts, above
15.
15 amps, supposedly. Okay, so it's this thing was meant to supply up to about 15 amps of current, and that's moving those needles. But did it move the needles very strong compared to that permanent magnet?
Not really.
Not really. So that you would think the magnetic field then made by this current is relatively weaker than the magnetic field in that permanent magnet. So our observation to start with has a qualitative element. First, we know that electric currents make magnetic fields. That's not qualitative. We've seen it. The next qualitative element is it doesn't seem like electric currents going through one wire make very much magnetic field. They make some, but they're not making a lot compared to the magnetic field of this magnet. Okay, so now, when the current flows through here, notice the size of this piece of copper. It's a big chunk, isn't it? And it's a lot bigger chunk than the size of the wire that's here. This wire is mostly insulation, and then is the copper inside it for the wire. Why do you suppose this guy is such a big piece of wire? So thick. First off, for physical rigidity, so that people bump it and use it and demonstrate with it, don't change its shape very much. So it needs mechanical strength. Secondly, if we put current through here, if there's resistivity in the copper, that means there's heating going on. And if you put a lot of current through this and leave it on for a long demonstration and forget to turn it off, this piece of copper will get quite hot. And you notice I did like that to check before. And it can melt the plastic here and ruin the demonstration. So the size of the wire probably was decided by trial and some error happening over time. Okay, now Jacob, flip the switch again and let's check the direction of the arrows. Okay, we got it. Turn it off. You got the direction of the arrows written down? From your view, I guess those arrows are going, what are they doing? We got to turn around here. They're going mostly clockwise. There's a couple of recalcitrant arrows, but mostly clockwise near the, let's try reversing the wires. So we're making the current flow in the opposite direction. Go ahead, Jacob, get ready, and throw the switch. Now which direction are they going? Counterclockwise. I guess the ones that stuck a little helped to kind of tap things, didn't it? So turn it off. Counterclockwise with the black connected to the red lead. And now we're going to, oh, here, feel that. Just squeeze it. Warmed up, huh? Mm-hmm. All right. Now we'll go back to red on red and black on the black connector. Okay, go ahead. And I'll tap it to help it. And now we are back to clockwise. And you see the clockwise. Okay, turn off. And yeah. So you can feel the warmth at the contact points, because at contact points the current has to flow through a very small area, and the resistive dissipation then, remember the resistance goes as 1 over the area, so there's a lot of resistance at points of contact where things connect. And so you get most of the heating that's readily observable in the wire was at these clips. Okay, Jacob, the excitement knows no bounds, and we're going to move to a different one doing the same kind of idea. Okay, now what we have here is a coil of wire, and if you take a look at it, you see how many turns are there? Can you come over there and maybe count how many turns of coil there are?
About 7 or so.
So 7 turns, say, okay? And it's made into a coil shape, isn't it? And we got two leads. Now these wires are a little smaller, aren't they? So let's see if we get an effect here. Okay, hit it. Okay, why don't you turn it off? And what did you see there? Hang on a sec. Okay, turn it back on. Ready to observe? It's a more complicated pattern, isn't it? We got 2 ovals. The one on your left has got clockwise motion. The one on your right has counterclockwise motion. Stop, 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 stop. And they add into the same direction going through the center. Let us thank Jacob for his outstanding work with magnetism. So, okay, so now what we've seen is by making a coil of wire, you can enhance the strength of the magnetic field because now we had like 7 turns of wire there instead of just 1. You can make more turns of the wire can help make stronger field. This made a dipole pattern instead of just 1 circle around the wire. We got a dipole pattern from this guy. So a coil of wire can make a dipole. All right, let's run this guy up. Okay. When I was coming in this morning, somebody asked me about the root mean square, the RMS. And it made me think, oh, this is very important, why we need to know that. So why use AC or DC for electric currents? Okay, so the A means alternating, and the D means direct, as in not alternating, as in steady, steady state. So, and the C, what's the C mean? Current, right? So current for the DC. So when we have some kind of circuit, we may have AC in it, we may have DC. So the AC could have, versus time, the current or the voltage, for example, may do something like this. This one is sinusoidal. It doesn't have to be this shape in time, but it's very common to do this, and it's relatively easy to make compared to other shapes. So this is sinusoidal. Changing in time, right? And the direct current versus time, we might have I or V, and it's steady. So steady. Unchanging. We call this steady state, if you want, sometimes. And that term gets used for other meanings in other applications as well. So if we have these two, why do we use one? Why do we use another? When to use? That's our question. When we go over to the wall in the house and plug something in, is it AC or DC?
It's AC.
AC, you've been told, although probably you haven't measured it as such. However, we did have a demonstration here which showed that was AC. Remember when we plugged the Jacob's ladder in and we made the spark? To your eye, the spark looked like it was steady. But when I drew a piece of paper through the arc, it had little stippling on the paper where it burned through at each on point for the arc. So the paper showed a graph of the arc versus time and showed it was going off and on and off and on. So what we saw then was that the box that the Jacob's ladder provided the power was plugged in to the floor here, and that caused an alternating current. So the voltage and the current that's in the wall typically, not always, but typically, is alternating current. On the other hand, what we just used here, when Jacob threw the switch, this power supply is powered by the wall, so it's got AC coming in, but when he threw the switch, the power over here to the coil was direct current, DC, unchanging in time, steady. So we've made a choice. So the choices are generation, and dissipation. Those are the things we want to consider when we do this. Now, if we go outside and you drive down a highway and you look off to the side and you see an electric power line. Yes, question?
If we plug that magnet thing directly into the sockets, would the little compasses be going crazy back and forth?
If we plug the magnet wire from this coil directly into the socket, would the little arrows be going crazy? Yes, they would. And they would be going crazy for two reasons. One is the current would be alternating, and so they'd be wanting to point one direction for part of the cycle and then try to flip and point the other direction for part of the cycle. And the other would be that the voltage is much bigger there than what the DC applied voltage was, so the current will be much larger also. And so that the effect would be much larger. And boy, that would be fun. Maybe we should try it sometime. However, the arrows being as large as they are, approaching, approaching a tenth of a gram maybe, their mass, and then their inertia, right? Make your arms into an arrow. Everybody do this. Stick your arms straight out. Don't get too friendly, right? And now if you try to wiggle holding this rigid, right, there's some inertia, some resistance to the turning. If you bring things in close, right, and go like this, it's much easier to rotate, okay? So as a result, the inertia of the arrow will make it hard to rotate on the time scale of this 60 cycles, okay? So it won't, the mass of it in combination with its distribution means the arrows may not wiggle very much because they'll have trouble. It's like if you come up and, punch an elephant, it's not going to move very far, right? It's got a lot of inertia. Well, it depends where you punch it, I suppose. Okay, they have sensitive noses, I understand. Okay, so now let's see. Generation means. If we use a battery, is it charged? How do you check them.
Do I want to do that right now?
That one's not very good. This one is getting a little on the old side, but it'll probably work.
You realize I'm doing it.
9 volts, right? Don't do it on a 45-volt battery. Okay, the biologic response is different. Okay, so anyway, that's a DC supply. The battery provides steady voltage across the leads for its intended operation. On the other hand, there are ways to make things rotate and turn on and off while rotating, and we're about to see how to do that over the course of these next 2 lectures, today and tomorrow. And we'll see that time-changing methods can be used to make voltages also. Okay, so now, back to driving your car. You're driving down the highway, and you look off to the side, and you see a very comforting sight, an electric power line. And if you were driving down the highway and you didn't see it, you'd go, uh-oh, we ran out of electricity. That would be a very disturbing moment for you. So when you see that power line, where is it? The power line is, say it again? In the sky. It's up on a tower, isn't it? Okay. Now that means somebody went to the trouble of building a tower and putting the wire up there. And then, oh, goodness sake, they went down the road a bit and built another tower and put the wire up on there, and then went down and did it again. That's not cheap. Would you like to go home this afternoon and build a power line tower for yourself? Your bank account would probably run out of money on the first tower. So there's been a collective decision that it's well worth it to build towers. Are these little monuments and then we worship the electricity gods up there on top of the tower? Yes? Okay. The reason we do that is, let's look at losses. So we have generation means. Batteries. What's the voltage on this battery? 9 volts. What's a typical voltage in a flashlight battery? What is the voltage your cell phones run on? I don't know. After this class, take your cell phone apart. Look at the battery and it will say usually what the voltage is and the amp hours, how much it can hold, right, for energy. Then once you've removed the battery, throw the rest away. Okay, does it say on yours, Cassidy?
Mine says, model, says rating 3.7 VDC.
What did that say?
3.7 VDC.
3.7 VDC, 3.7 volts direct current. Okay, so you got a 3.7 volt phone.
Yes.
Okay, yeah. The voltages are going down on them over time for a good reason. Okay, so now that means that batteries are typically things that make 1 volt, 10 volts, somewhere in this range, and to make voltages higher than that is hard to do. DC voltage is easy to make at low voltage. Okay? However, DC voltage is not so easy to make at high voltage. power losses, power dissipation. So here's our source. So let's see. This is the hamster wheel. So this is the source of the energy, right? And then it goes along, and we have our poles, our power pole. Another pole, and then another pole, and then finally, here is the load. Our intended use, right? The use, the refrigerator, charging your cell phone, running the lights. This is the load. And so we're doing something like this. There's a resistor shown here. And that's where we want to be using the power. But there's a wire running along there, and there's also the ground, the earth, right? Nearby. And what we've done is put those wires up into the air. As we push current down the wire itself has resistivity, some resistivity. So there is an unintended power dissipation. Power lost, right? It's going to be I times V down the load is going to be I squared R, or V squared over R, and this is R of the wire, or the loss. There's a resistance here, a loss resistance, which is not the load. Let's look at that V squared over R. If I want to deliver power at the load, we have a choice there. We want to get a certain amount of power to that load. If I want to do that, I'm going to have a little bit of carrying charge here. There's going to be a loss coming down the line. Whether I use AC or DC, the loss in the line has the same resistance. There's no preference for AC or DC based on the resistance of the wire. However, there's another term here, V. V squared is upstairs. If I want to deliver the same amount of power, I can have a higher voltage up here if I run AC. Because I can have a higher voltage there, then I can run down the line and have more power delivered with less in the loss as a result. So I can run a lower current and a higher voltage, and I can make that AC at a high voltage. I can't make DC at a high voltage. Notice that the wires are pushed up from the ground. If we put the wires down by the ground, so we have resistive loss, and capacitive issues. If we have the wire up in the air, to push the charge down the line, we have to charge the line. So we have to put some charge into it. The line has a capacitance, and we can do that. If we're doing it AC, we've got to do that every half cycle. We've got to flip the charge. So there's issues with doing the work with the capacitance that's an issue. There also is another one. But let's do this to start. If I bring the wire down close to the ground, Now, surrounding the wire is ground, a dielectric material, which will change the capacitance of the system and increases the capacitance of the system. So it takes more work to put the charge on the line, AC, if it's close to the ground. So we go AC to get high voltage, low current, so we have small losses. We go up in the air to reduce the capacitive and inductive losses. And we haven't quite got the inductive part figured out. So this is this lecture and the next one. What we will find is that time-changing magnetic fields induce currents. So if you have a time-changing magnetic field from the current in the wire, it will induce a current in the ground, which causes resistive losses in the ground. So if we want to have AC, we need to have it up in the air. On the other hand, you can't always be up in the air, can you? Sometimes you want to be underground. Where's a place where we want the wires underground? In a city, where everything's space is very valuable, and so underneath the ground is used a lot. In a city, it would be good to put the wires underground. So in a short distance, DC works better. And in a short distance, DC is valuable to use. When we got power started, electric power started about 120 years ago. It's only that old. When we got started, Thomas Edison promoted DC. And New York City, part of Manhattan, was the first place lit on a large scale. And that was with a DC power station, steady state. Those power stations had to be within roughly 1 or 2 kilometers of where the light bulbs were. And Edison promoted DC. Well, a guy named Tesla, Nikola Tesla, decided that AC was better. And he promoted AC. In fact, he worked for Edison, I believe, for a while. And then they got cranky with each other and split. So Tesla went off and did AC, but needed money. So he got George Westinghouse. Westinghouse was a very powerful inventor and pretty good businessman. And those two guys decided to make AC power. So the AC versus DC was the competition there. And whose name do you see on all the power companies these days? Edison, right? He lost. Tesla's idea won resoundingly and has been the dominant form of power consumption in the United States. I think probably around 90% of all power is consumed using AC. And so Tesla and Westinghouse started up the company. And let's see, Edison was kicked out of the company after a while. And then the company was changed into a different company with Edison not involved with it, I believe. And it was called General Electric, which is arguably the biggest company in the world. And so General Electric was the result of that. Okay, so on another place where you would like to have underground is if it's going underwater. Submarine cables must be underground. So at that point, then if you go under a river out to an island or something like that, DC is better, because it doesn't have as much dissipative losses. And in the intervening 100 years, making high voltage DC has become much more possible. It's still not really viable in a lot of circumstances, but it's coming back. So you see a mix of both of them, but we use AC because of these dissipation losses and the ease of generating the high voltage AC. Okay, so I don't remember who asked that question about RMS, root mean square, but the reason we need to know about root mean square is because we want to use this sinusoidal kind of wave a lot. We really use it a great deal. So thank you for asking, whoever asked that. Okay, back to magnets then. So magnetic fields are created by moving charges. So moving charges makes a magnetic field. The element of magnetic field made by a moving charge goes like this. And this is not an easy equation to think of. I'm going to write it a different way. What we have is some charge moving at some velocity, and we're looking over at some point P. So the direction I'm choosing for r hat is this way, from the moving charge to the observation point. Either way that I've written this, this is a complicated equation, isn't it? We've got a v cross r over r squared with an r hat here. We got a v cross r over r cubed with an r vector there. You will see this equation written either way. It's the same either way. And what it says is that moving charges create magnetic fields. Doesn't this look like a 1 over r squared kind of effect? Here's the 1 over r squared, like Coulomb's law. But we have to remember there's a sign of theta involved in that cross product. These two equations I've written are identical in physical interpretation. R hat is a unit vector, magnitude 1, pointing in the direction of r, whereas r here has the magnitude of r pointing in that same direction. So given that there's an extra magnitude of r upstairs, there's an extra one downstairs to kill it off. So if you look at the equation on the right, the magnetic field creation does not go as 1 over r cubed. It goes as 1 over r squared. You have to be careful looking at the top and the bottom. Both the denominator and the numerator matter. This way of expressing it is a little clearer to show the 1 over r squared effect. You see it visually with the 2 in the equation. So I tend to like to think of it that way. Q times V. That's the charge times its speed. So this is the microscopic view. Microscopic view. And instead we might want to think of a macroscopic having a chunk of wire, a bit of wire. And it's got some length to it. And inside it is carrying some current. And so that we could say that the wire points this way if we want to, give it a direction. And there's a current flowing in this. So on the macroscopic view, Q times V just becomes I dl. They are the same. The amount of charge flowing in that chunk gives us the same. So you can write this as mu naught over 4 pi I dl cross r over r squared if you like instead. There are now 3 ways to write this equation, and you will see it all of those ways. What we're seeing here then is an equivalent to Coulomb's law in its sense as applied to what we've discovered about magnetic fields. This quantity mu naught, this constant there, is 4 pi times 10 to the minus 7, and then the units, oh goodness, I'm going to say Tesla per meter amp. I'm not sure if I got the units right. Maybe it should be a meter squared. No. I think that's probably right. Okay, so notice that this, whoa, 10 to the minus 7. 10 to the minus 7, small. That's a small number. I, in amps, the current per second passing through some area. A typical current we have is 1 amp. A typical distance we might measure away from a wire, 1 meter. And so if we put in ones everywhere, what do we get out for B? We get, other than that factor of 4 pi, we got a 10 to the minus 7 hanging in there and not going away. Amperes. So that means that you don't get many Tesla per amp. Magnetic field is hard to make with currents. So not many Tesla per amp produced. And that fact is represented in how small mu naught is. That reminds us that you don't get much. Tesla, the unit of magnetic field that we use these days is Tesla, as in Nikola Tesla, as in the guy I was just talking about. Somehow I'm thinking he spent a good deal of his life around Pittsburgh. I think he was born in Croatia and then came to the US and lived mostly around Pittsburgh. I'm thinking that because I think that's where Westinghouse was also. Okay. And where was Edison? New Jersey, Menlo Park, New Jersey. Inventing away there, really, really hard all the time. Very bright guy. Okay. And Tesla, curiously, then, was in some ways much more modest. And I believe gave his AC patents to Westinghouse for free because he wanted them to change the world. And he didn't care about the wealth as much as other people. So Tesla was an unusually productive and inventive guy. So we make our magnetic fields and we don't get very much. So if we put in 1 meter per second, and one meter distance and that kind of stuff, and the Q is small, we just don't get very much Gauss per amp. Okay, so that's the Coulomb equivalent, and now we can have Let's have a Gauss's law equivalent. Is there a Gauss's law equivalent? I'm not sure why we use the B for magnetic field, but I'm going to make a guess that it's for BO, as in Biot-Savart, the law that's named for this. Let's look at a current coming out of coming out of the paper. Suppose we got a current coming straight out, and so it's like the point of an arrow is coming towards you, and I draw the current coming out. So here's the current coming out. If I wanted to draw the current going into the board, what would I do then? Look at the other end of the arrow, right? Just for comparison, this would be into the board, right? Into the board, the back end of an arrow. So that's the tail end where you see the feathers, or as we discussed before, the fletching on the arrow. If we have the current coming straight out, we have our observation already. We had current coming straight out in the demonstration we just did, and it made a magnetic field. That had this kind of shape around it. And the magnetic field got weaker as we went further out. Stronger inside and weaker going further out. Gauss's law for electricity, integral E dot, do you want a dA or a ds? What do you guys like? The charge that's enclosed divided by epsilon naught. And, huh? Okay, he wants a dA. Are you like that one? You cool with that? Okay, we wrote that one for Canadians. Okay, so now what this says, an integral, we recognize that, and then it has this little closed circle on it, which tells us, something's closed. And then we look over to here, and we see a closed surface, right? So we recognize surface. We see that dot. What's that tell us? Yeah, there's a cosine coming in. That's a good thing, good way to think of it, right? And E, what's E? The electric field. And this says that electric charges make electric fields. And it tells us the contribution to the total electric field from the enclosed charges. Once again, it does not tell us the total electric field. And then there's an epsilon naught. Is epsilon naught a small number? Yeah, but epsilon naught is downstairs in that equation. So it says electric charges are real good at making electric fields. Okay? So there's our, let's see if we can come up with something. Maybe a little BS. Would that be the right thing to do? Let's do a little, no, I'm going to do an L here. No, let's do an S. Let's do the BS one first. Does that look like BS to you? Okay, now let's think about this. Now I've just changed the electric field into magnetic field. I changed that. We could put a dA here if you want. Okay, you put a dA there because you'll be more comfortable. Okay? Now, this said that electric charges make electric fields. Everywhere we've been doing the demonstrations here, there's a current that comes along and goes in one place and goes out another place. It doesn't have a magnetic charge. There isn't a monopole of magnetism. We got current comes in somewhere, goes out the other side. It doesn't just sit around. This magnet has two poles, not one. So there are no magnetic charges that we've observed. That tells us this equation doesn't help us. Magnetic field going in somewhere comes out the other side. Let's try a different one. And now what I want to do is pick a path. Let's do a path. This current is what's coming out of the board there at the center. Let's do a little path that's like this. Okay? That path that I've drawn is parallel to the magnetic field there. So since it's parallel, if I go B dot dl, what happens to the dot? 1. Okay. And it's not 0. It adds up here, it adds up here, adds up here, adds up all along there, doesn't it? And if we add it all up, we arrive at this guy. If you add it up going all around the circle, you get B is the same everywhere. Example. See the circle. See circle drawing. Right? We've got our I coming out. Here's B and dl. So I've got integral B dot dl equals mu naught I. That's B times 2 pi. Oh, how far out is it? R equals mu naught I. Says that if I use that equation, it predicts a magnetic field of mu naught I over 2 pi r, which is exactly what you get if you add it up by doing this contribution of B everywhere due to individual pieces of current and then figure it out. So this is called Ampere's law. As opposed to Gauss's law. And Gauss's law for magnetism isn't terribly useful for us, other than saying that there's no source or end to a magnetic field. All of these magnetic field lines come around and bite themselves on the tail from the way the drawing is shown there. Okay, let's do some more demonstrations. You've helped. Have you helped? Come on up. Okay, shall we start with this one? And you are?
Sure, Nicole.
Nicole, hi, Roger McWilliams. Let's see. Can you do, what's lying on the table?
Looks like aluminum.
Aluminum foil. The thrill is never ending in this class. A piece of aluminum foil. Okay, throw the switch, Nicole. Okay, turn it off. Now we'll reverse the leads because that was so dull. Okay. Can you do that one? Squeeze it, yeah, and then it's an alligator clip. You see why? Because it looks like an alligator, doesn't it? Okay, now throw the switch. Whoa! Okay. Good reaction. Okay, what happened? Everybody's got so excited seeing everybody jump. Now, once you watch that and then throw the switch again. Okay, turn it off. Okay, let's see. Newton's laws. F equals dp dt equals ma. Aluminum foil. Got accelerated upward, didn't it? More than More than enough to overcome gravity. What was the upward acceleration? Show them again, Nicole. Down. How long did it take to get there?
Maybe a second.
Do it again, Nicole. Yeah?
Less than a second.
Less than a second, huh? Okay, go for it. Okay. Let's see if we can cut the. Try it like that. Oh. If it has to pull the mass in of the entire length of the foil, it takes longer to pull it up, doesn't it? And if we've got it kind of crinkle less mass that way, go ahead and do it a shot. Very quick. Maybe 1/10 of a second when 1/10 the mass is involved. How much mass is involved? Oh, curses. Foiled again. What is it? It's a... Describe to them. What is it?
Is it?
Yeah.
Oh, it's like a few layers
It's
of aluminum
a
foil.
few layers. Now, let's get quantitative.
layers.
Keep going. Open her up.
Oh, wow. No, it's gonna rip.
Yeah, so what? Oh, but then we won't know how many layers, huh? I'm going to do one here, too. Uno. Dos, tres.
Three.
3 layers. 3 layers thick. And how far across is each layer? About how many centimeters here?
I'm not good with approximations.
Put a finger down there.
Okay.
Okay, 5 fingers wide?
Yes.
Okay, so we got 5 centimeters across, 3 layers. How thick is aluminum foil? Ah, is it a meter thick? Is it a centimeter thick? Is it a millimeter thick? Getting closer, but still not going to send you out to buy aluminum foil at a millimeter thick. Okay, so this stuff is pretty thin, isn't it? And that's why if you were thinking, oh God, he's going to ask me to tell me what the mass is, it's really small, isn't it?
Nope.
Okay, so we have 3 things of aluminum foil thick, and you have to find out by going to the grocery store, don't you? And figuring it out. And then it lifted that up. So, currents felt forces from magnetic fields, right? Just what we've been writing up here. Now let's take a look over here. This is the excitement. Oh, okay, so I'm going to be little Dr. Frankenstein. And you're Nicole, okay? Okay, oh, my back. Ugh. What do we see here? What's it called?
Die hard.
Die Hard. It's a battery. It's a Bruce Willis battery. Okay, it's a battery, right? You see the plus and minus?
Yeah.
And it's a car battery, right? And those are there to indicate which is positive and which is negative for the terminals. We have red and black hooked up, and then the giant switch. Oh, throw the switch. Throw the switch.
Are you sure?
Yeah, of course. I'm standing away from it. That was pretty exciting. Let's see. Whoa! Come over here. Feel that.
I'm scared.
You should be.
Oh, it's just warm.
It's just warm. You go stand there a second.
No.
Yeah. Are we ready? Don't touch it.
I'm going to.
Now touch it.
Are you sure?
Yeah.
It's getting warmer.
Getting warmer. What was the direction of the motion of the... That's as dull as it could be. Let's try reversing. Go, oh, that's getting hot. Come on. There's one. Can you hold that? Okay. Now I reverse the direction of the leads on one of them. Nicole, throw the switch. Okay, enough. Up. Now what happened? Attracted, right? One direction of current flow attracted and the other one kind of pushed away, but not so dramatically. So one direction of currents relative to the other. And which way is that? Do we know? Let's see if the reds go on back to where they feel like, yeah, they're on the same side. Okay, so now we have like currents. Like currents. Both currents are going the same direction from positive to negative, flowing that way, and show them. Okay. Now I want you to observe right in here when you do
There's
the
a spark.
Yes. Go ahead. And a pretty good sized one, isn't it? So on release and on connection, both contact and release, there's a spark. Okay? And Joule heating. Can you calculate how much Joule heating? What's the voltage in the battery? You guys know? 12 volts. It's a 12-volt battery. They typically charge a little over 13, but let's call it, they're called 12-volt batteries. So let's 12 volts on the battery. Can you tell me what the resistance in the foil is? Oh, we need to know how many layers again, don't we? It's probably 3, you think? Oh, they're so careful the way they did this. They won't like me afterwards. Okay, 3, the same, right? As what Nicole just did over there. So we got kind of the same on both circumstances. So 3 on the foil, and so like currents attracted and opposite currents repelled. Is the excitement over? Oh, here's the one more we can do. Here, come on over here. Magnet, right? You got it? Can you hold that? Coil, okay. You got that? Little 9-volter, okay. You ready?
Ready.
Don't drop that magnet,
Okay.
because you're wearing sandals. You'll break your toe.
All right.
You ready?
Ready.
Was that fun?
That was pretty fun.
Yeah. Was that? You're hoping there's more excitement in the day, aren't you? Let's see if that's not gonna work there. Okay, hold it. Yeah, just put your hand there to hold it. Just to grab right around there. We'll use your hand as a rest. Further up, right there. Okay, are we ready?
Whoa.
What's it want to do there?
Go back.
Okay, just okay. What did it do there? What did I do? I reversed the direction of my wiring. Okay, ready?
Ready.
Oh, nice bad battery. Okay, here we go. I got wiring one direction. That was that way, right? Uh-oh. Let's get it where it attracts to start. Okay. This way, it's going to pull it down. Ready? Okay. Now I'm going to reverse and flings it away. We have an electromagnetic accelerator, don't we? The excitement continues. Nicole, outstanding job. Thank you, everybody. See you guys tomorrow morning, to be continued.